But the remainder of this pack is concerned with loci of complex numbers. Loci is something you should have met at GCSE before. Locus of points, essentially all the points that are equidistant from various different things. So you can have a locus around a single point. You can have a locus between 2 points and all sorts of different things. There are 3 types of loci that you need to know about for complex numbers. You need to know about circles, which is the first type we're going to look at, perpendicular bisectors, and half lines. To recognize that something is represented by a circle in complex numbers, it will have this form here where it's modulus of z equals some constant. Okay, so this is saying it wants all of the complex numbers that have a modulus of 3. You will want to use a compass for these or draw a coin or something, and you'll want a compass to take into your exams to draw these ones. So this one is just represented by all of the points that have a modulus of 3, which is anything that lies on this circle that has radius 3 and is centered on the origin. So we've got 3 here, 3i up here, minus 3i down here, minus 3 over here. All the complex numbers that lie on this circle will have a modulus of 3. Similarly for the U-tri, it's just a circle centered on the origin with modulus of 2, radius 2. Now it's usually more complicated than this. It's usually something of this form here, z minus z1 equals r, where z1 is the center of the circle and r is the radius of the circle. With a bit of algebra, we can show that this is a circle. So if we let z x plus y and z1 is x1 plus y1, we can substitute those into there. So we've got x plus y minus x plus x1 y1 equals r. We collect up the real parts inside this modulus sign here, and we collect up the imaginary parts. We get this. You know how to do the modulus of a complex number, so it's the real part squared plus the imaginary part squared. Remember, you don't include the I when you do that, and square root that. That's how you calculate the modulus of a complex number, and that's equal to r. If I square both sides, you can see now that this is in the form of a Cartesian equation of a circle. The center of which is x1, y1, which are the coordinates of z1, and the radius is just r. You won't be required to do that in an exam, but it's just to demonstrate that if you've got a locus in the form modulus z minus z1 equals r, that's a circle. Note the minus between z and z1. So this is saying that all of the complex numbers where the distance between them, z minus z1, is equal to r. That's why it's a circle. To be able to draw these, you have to put these into the form z minus something. So this one is modulus of z plus 2i. I need to change that to be z minus something. So it needs to be z minus 2i equals 2. This is a circle centered on minus 2i with a radius of 2. You must always think carefully about where your circle should cross the axes. Will it go through the origin, etc.? And in this case, it will, because it's centers at minus 2i and it's got radius of 2. So this will go through the origin and it'll go down to minus 4i total. Similarly for this one, again, it needs rewriting as modulus z minus something. The change in the signs on the 1 minus 2. So z minus 1 plus 2i equals 2. So the center of this circle is at minus 1, 2i, so up here. This is a circle of radius 2. So thinking about this, I've gone up by 2 and it's got radius of 2, so I should just touch the x-axis down here. And I'm going to label up the easiest points. So I'm at minus 1, 2 up here. I'm touching at minus 1 down there. We've got radius 2. Pause the video now and have a go at those U-tris, please, and I'll reveal the answer in a sec. So for this first one, it's a circle centered on -3i. It won't cross the x-axis because it's only got radius 2, so it'll cross the y-axis at -1 and -5. Down here does need rewriting, even though it said minus, that needs to be in a bracket, so it should be z -1 plus 3i, which is where the center is. It's got radius 2, so it will cross the y-axis, but won't cross the x-axis. It's sometimes useful to represent loci with their Cartesian equations. So we need to identify what this one is. I'm going to write it as z minus something. Although it's a minus, that needs to be in a bracket. So z -2 -3i. This is a circle, center of which is 2 -3. And the radius is just 3. Careful with that, because in Cartesian form it's usually r², but that 3 is just equal to the radius. Using this information, we can put it into Cartesian form. So our equation is x -2 squared plus y plus 3 squared equals r², which is 9. Have a go at the u-try, and again, I'll pop the answer in a second. So rewriting the locus as z minus -2 plus 3i tells you the center's at -2, 3, and the radius is 5, which you can stick into the Cartesian form to get your x plus 2 squared plus y minus 3 squared equals 25. The second type of loci you need to know about are half-lines. So half-lines are unique because these are to do with arguments rather than moduli. These are all the complex numbers which have a particular argument. So for example here, this is the locus of points of all the complex numbers which have an argument of pi/6. This is going to start from the origin. Pi/6 is 30 degrees. So it's going to go something like that. It's a half-line because it doesn't extend past the origin. Complex numbers to the left of the origin would not have argument pi/6. It's only these ones here. You don't need an arrow on if you don't want to. This angle in here, measured from the positive real axis, is pi/6. Please draw the u-try one. I'll reveal the answer in a second. So this one again, starting from the origin, it's going to the left this time because 3π/4 is obtuse. It's 135 degrees. So going that way there. Again, half line starting at the origin doesn't go through the origin. This gap in here says half line. Similarly to circles, we need to write them in the form argz minus z1 if they don't start at the origin, where z1 is the point where this half line originates. The angle is always measured from the positive horizontal and measured anti-clockwise, just like we do from the real axis. To find the Cartesian equation of a half-line, you know a point that it goes through. You know it goes through the coordinates of z1. To work out the gradient of that line, you do tan of an argument, and that will give you the gradient. We'll look at that later on. So for this first one, sketch the locus of points which argz -2i equals pi/4. We don't need to do anything with this one because it is argz minus a complex number. So that means that it starts at 2i, not -2i. So it starts at 2i on the imaginary axis. The pi/4 we measure from the positive horizontal. Pi/4 is 45, so it goes something like this. Half length, it doesn't go through the 2i. Have a go at the u-try, and I'll pop the answer up in a sec. So this one does need rewriting. It needs rewriting as argz minus -2i. 2π/3. So we're starting at -2i on the y-axis. 2π/3 is an obtuse angle. So pi/3 is 60, so 2π/3 is 120. So it goes something like that up there. And it's a half line, doesn't go through the -2. For this next example, it wants us to actually, going back to these, it asks for the Cartesian equations of these as well. So for the Cartesian equation, I know a point that this one goes through, which is 0, 2. I need to know its gradient, which is just given by tan theta. So it's given by tan over 4, which in this case is 1. So using y minus y1 equals mx minus x1, goes through 0, 2. So y minus 2 equals m1 x minus 0. And we get the Cartesian equation is x 2. This technically is only valid for positive x in here. So to the right of the original coordinate. I'm going to say x is greater than equal to 3. Actually, strictly greater than it should be, because the point at equal to 0, 1 have that argument pi over 4. For the u try one, same things. If we work out the gradient, so that m is tan of 2 pi over 3. That gives us minus root 3 for the gradient. Point it goes through is 0 minus 2. So y minus y1 equals m x minus x1 gives us the Cartesian equation of minus root 3x minus 2. This time only valid for x is less than 0 to the left of this point here. So for this example, I do need to do some working out first. So I need to write it as z minus a complex number. Changing the signs on these points gives me z minus 2 plus 2i over 4. So this is starting at the point minus 2 plus 2i somewhere here. Angles measured from the positive horizontal, and it's pi over 4, which again is 45. We go something like this. For the Cartesian equation of this one, again, the gradient is 1. The point it goes through is y minus y1, which is 2. So mx minus x1, which is minus 2. Gives us the Cartesian equation. This is y equals x plus 4. And again, this is only valid for x is to the right of this point, which is greater than minus 2 this time. I will go at the u try and I'll pause this. I'll reveal the answer in a sec. So this one needs rewriting as arg z minus 3 plus 2i. That's where the original point is. Angles measured from the positive horizontal, so draw the dotted line in. This time it's minus pi over 3, so it'll be below that line there. Pi over 3 is 60. For the Cartesian equation of this one, the gradient will be tan of minus pi over 3. It's also minus root 3. So we've got y minus y1 equals m x minus x1, and that gives us minus root 3 x minus 3 root 3 plus 2, and this time it's only valid for x is bigger than minus 3, x to the right of that minus 3. We can show this algebraically, so suppose we've got argument of z minus z1 equals some angle theta. Doing the same things we did for the circles, we can write z as x plus iy and z1 as x1 plus iy. We collect up the real and imaginary parts. So real parts, we've got x minus x1. Imaginary parts, we've got y minus y1. And then we're going to calculate the argument of this complex number here. So to calculate the argument of a complex number, remember if you've got a generic one here, we use trig, where y is your opposite side and x is your adjacent side. So your imaginary part's opposite, your real part is the adjacent. So that tells us that tan of theta, and then here, it's opposite over adjacent, so it's y minus y1 over x minus x1. And if we times it by the bottom, That's where this all comes from. The final type of locus you need to know about is perpendicular bisector. So these look similar to circles, but are different because you've got a modulus on either side of the equation. Just like the other two that we've done, they need writing as z minus the complex number if they're not already in that form. And this will be the perpendicular bisector between these 2 points, z1 and z2. So these are all points that are equidistant from z1 and z2. This first example is in the form that we need it to be in. That's minus after both of those sets. So this is the perpendicular bisector between the point 2, the real axis, and the point 2i, the imaginary axis. Draw a dotted line between them. The perpendicular bisector goes through those two there. It's just a sketch, so this one should have gradient of 1 because they're symmetrical. Have we got the U try, and then I'll do the answer in a sec. This one does need rewriting. The right-hand side needs rewriting as z minus 4i. So this is the perpendicular bisector between the origin from the left-hand side and minus 4i on the right-hand side. This is just a horizontal line at -2. Bit of a trickier one. So we're sketching this locus and finding the Cartesian equation. First thing to do is rewrite this. Mod z minus 3i plus mod z minus 2i. So this is the perpendicular bisector between the point -3 which is down here somewhere, and the point -2i, which is down here. The perpendicular bisector will go through the midpoint of that, so something like that ish. We'll work out the equation of this in the same way as you would in Cartesian coordinates. So we'll find the gradient of the segment joining those 2 points, we'll find the midpoint and go from there. So the gradient between those 2 points is change in y over change in x. So make sure you're consistent with that. So I've started with -2, 0 minus 2, which will give us a gradient of a third. So the perpendicular gradient of this, if it changes sign, is -3. Point it goes through is the midpoint, so the average of those coordinates, so 0 plus -3 and -2. 2 gives me that's the point, -3 over 2, -5 over 2. We can now do the Cartesian equation. So I've got y minus y1 equals mx minus x1. Hasn't specified what form it is to be in. So this is y equals -3x minus 7.